So this is the physical science lesson video for section 10.2, and as always, if you'd like to subscribe to my channel, you'll have all my videos for the whole year. So we're going to continue talking about nuclear chemistry. So we talked about alpha, beta, gamma in the previous video, so now we're going to talk about the rate of nuclear decay. So how fast is that nucleus either releasing energy or releasing charged particles? So every radioisotope decays at a specific rate that can be expressed as a half-life. A half-life is the time required for 1/2 of a sample of a radioisotope to decay. When we say decay, we mean release the charged particles and energy that we talked about in section 10.1. After one half-life, half of the atoms in a radioactive sample have decayed, while the other half remain unchanged. Now, a lot of you then like to think, well, then after 2 half-lives, it must all have decayed. But that's not the way it works. So let's say we start with 1,000 particles. After one half-life, half of those particles would have decayed, so we'd be left with 500. After another half-life, half of the 500 particles would have decayed, so we'd be down to 250, like that. So it's not like half decay, that's one half-life, the other complete half decay. Every time one half decays, you start with that amount to decide what your next half would be. Okay, so like we would go 1,000, 500, 250, 125, like that. So unlike chemical reactions, if you watched some of the previous lesson videos, we talked about ways you can speed up a chemical reaction. They vary with the conditions, so like I can stir or add a catalyst or something like that to change the rate of a chemical reaction. Nuclear decay rates are constant, so there's no way to speed them up, slow them down, anything like that. So how can we calculate half-lives? Well, we use the following formula. The number of half-lives equals the total time of decay divided by one half-life. So if we know a half-life is 1 hour, and we know 3 hours have passed, 3 divided by 1 means 3 half-lives have passed, like that. And so again, like let's say we're starting with 100. Well, if 3 half-lives pass, that means I'm going to half it, so I'd have 50 after one half-life. I'll half it again. So I'd have 25 after 2 half-lives, and then I'd half it again, so that means I'd have 12.5 after 3 half-lives. So if a question asked me after, 3 hours of time, how much do you have left, it would be the 12.5, like that. So, sample problem. Suppose you have a 1 gram sample of iridium-182, which undergoes beta decay with a half-life of 15 minutes. All right, so we know we have a half-life of 15 minutes. This is my half-life. After 45 minutes, so this is my total time, how much iridium-182 will remain in the sample? Okay, so remember our number of half-lives equals my total time over one half-life. So my total time is 45 minutes. One half-life is 15 minutes. So of course minutes cancel. So that means 3 half-lives have passed. 3 half-lives. So we're starting with 1 gram. So in other words, I need to half it 3 times. Okay, so we start with 1 gram and I cut that in half. I divide by 2. That gives me 0.5 grams. So that's after 1 half-life. So I cut it in half again. That gives me 0.25 grams. So that's after 2 half-lives, but we gotta go 3. So I cut it in half again. That gives me 0.125 grams. So after 3 half-lives, I'm left with 125 grams. All right, so hopefully you understand that. Sometimes it takes a little bit of practice with these. But we'll look at a couple more. Alright, and there we go, our 0.125. So, radioactive dating. In radiocarbon dating, the age of an object is determined by comparing the object's carbon-14 levels with carbon-14 levels in the atmosphere. Because atmospheric levels of carbon-14 can change over time, the calculated age of a fossil is not totally accurate. Alright, so we can use carbon dating, sometimes is what it's usually called instead of radiocarbon dating, to measure carbon-14. Okay, carbon-14 is a specific isotope of carbon, clearly. But the problem is it can only date specific things. Like when something gets too old, it's just not really accurate anymore. So to get an accurate radiocarbon date, scientists compare the radiocarbon, the carbon-14 levels in a sample of carbon-14 to the object of known age. So like if I know this is 1,000 years old and I measure its carbon-14 levels, and I don't know how old this is and I measure its carbon-14 levels and they're the same, then the objects are probably close to the same age. However, like I told you, it can only go to a certain distance in the past. So objects older than 50,000 years contain too little carbon-14 to be measured. So at that point, there's just not enough left because of that radioactive decay for us to be able to accurately date it. So, section assessment. How are nuclear decay rates different from chemical reaction rates? Chemical reaction rates can be changed based on the conditions, like concentration and things like that. Nuclear decay rates are constant. Nuclear decay rates are constant. Number 2, how can scientists determine the age of an object that contains carbon-14? They compare the carbon-14 levels to an object of known age. They can compare the carbon-14 levels to an object of known age. Number 3, if a radioactive sample has decayed until only 1/8 of the original sample remains unchanged, how many half-lives have elapsed? Alright, so it's saying that we have 1/8 left. So let's see what happens. Alright, so after 1 half-life, we would obviously have half left. Alright, if I take it and I have another half, that's going to be 1/4. If I take it and I half it again, that's going to be 1/8. So how many half-lives have passed? 3. Okay, so if you know the fraction of what's left, the 1/8, you can just multiply half times half times half times half until you get that fraction. So if it had said 1/4 was left, I would say, oh, okay, well 2 half-lives have passed. If it had said 1/16 was left, I would say, okay, well times 1 more half, that would be 1/16, and so then I would realize that 4 half-lives have passed. Again, half-lives take a little bit of practice, but you'll get it. So number 4, can radiocarbon dating be used to determine the age of dinosaur fossils? Well, dinosaur fossils are probably going to be really, really old, and so remember, it's only really accurate to about 50,000 years. So most likely some of those dinosaur fossils are going to be too old to have enough carbon-14 left for measuring. And number 5, a certain isotope of technetium has a half-life of 6 hours. If it is given to a patient as part of a medical procedure, what fraction of the radioisotope remains in the body after 1 day? Okay, so here's our half-life, and our total time is 1 day, which, let's get our units the same. So 1 day would be 24 hours. That's our total time. So remember, to get the number of half-lives that have happened, we do total time divided by half-life. So our total time is 24 hours over a half-life of 6 hours. So that means 4 half-lives have passed. Alright, so it says what fraction of the radioisotope remains in the body. So we just need to do half 4 times. So after 1 half-life, half would be left. After 2 half-lives, we lose another half. And then we would divide it by 2 again for our 3rd half-life, and divide it by 2 again for our 4th half-life. So 2 times 2 times 2 times 2, 2 times 2 is 4, times 2 is 8, times 2 is 16. So 1/16 would be left. Okay, so if you don't have an actual starting amount and they just ask you about the fraction, just divide by 2 over and over again until you get to that many half-lives. So 4 half-lives. Alright, so hopefully, I think that's the end. Let me just double check. Yep, it is. So hopefully now you understand a little bit more about nuclear decay, half-lives, and carbon dating.